Okay, in this video we're going to look at quite a number of examples of groups and some things which aren't groups as well. And to start off, we're going to look at some additive and multiplicative groups. So that means groups in which the group operation is some kind of addition or some kind of multiplication. So you can see at the bottom there I've copied our group axioms from the previous video, because those are the things that we're going to have to verify if we want to know whether a particular set with a particular binary operation is or isn't a group. Okay, so we'll start off with the simplest example of a group we can, which is the integers under addition. So if I take the integers z together with the binary operation plus, this thing is a group. Okay, so if we want to check that, we need to just check each of these three axioms in turn. So the first axiom is the identity, ID for short, and that says there should be an element, lowercase e, called the identity element, such that e star g and g star e are equal to g no matter what g is. So for us, we're looking for an integer such that when you add it to any other integer, you don't change that integer. Well, luckily for us, there is an integer with that property, namely 0. So 0 is the identity, and the reason for that is that for all integers lowercase z, we have 0 plus z, and z plus 0 are both equal to z. Okay, so the identity axiom holds, and the identity element, the lowercase e in the description of the axiom down at the bottom of the screen there, is 0. Okay, the next axiom is about inverses. Alright, so what we need for each integer lowercase g, we need another integer h, such that g plus h, or h plus g, is equal to the identity, which we know to be 0. So of course, if g is an integer, then minus g is an integer as well, and when you add g and minus g, you'll get the identity 0. So the inverses axiom is going to be true because for every integer g, there is another integer minus g. Let's write this down. If g is an integer, then minus g is also an integer, and g plus minus g and minus g plus g are both equal to our identity element 0. So the inverses axiom is true. And finally, associativity. Well, integer addition is associative, so it is a property, a general property of the integers, that if a and b and c, let's say, are integers, then a plus b plus c really is equal to a plus b plus c. So this is a standard property of integer arithmetic. Okay, so there is our first group, the integers under addition. Now, of course, similarly, you can show that all kinds of things form a group under addition. So let's say similarly, if we take the real numbers under addition, that will be a group too. And of course, the complex numbers. Generalizing this a bit further, if we take column vectors of height n with real entries, that has a notion of addition too. And so do complex column vectors, and sets of matrices Okay, so all these things are groups. And you'll sometimes see these called additive groups because the group operation for these groups is some kind of addition. Alright, so there are some things which are groups. Let's look at something which is not a group. So if we take the natural numbers together with the binary operation addition, well, addition really is a binary operation on the set of natural numbers n. So remember, that means the set 0, 1, 2, 3, and so on. But this is not a group. So the problem there is not the identity axiom. It does contain an element which satisfies the identity axiom, namely 0. So for the same reason that 0 served as an identity element for the integers under addition, it would also be an identity element for the natural numbers under addition. So that's not the problem, but the problem is inverses. So, for example, there is no element of the natural numbers such that z plus 1 and 1 plus z are equal to 0. So that means the inverses axiom is false for the natural numbers with the binary operation plus. Okay, so let's look at another non-group. We will take this time the set to be the set of all real numbers and the binary operation to be the binary operation of multiplication. So again, the identity axiom is true for this set and binary operation. So it has an identity. It's got an identity element, and of course that identity element is 1. And in fact, this is the only possible choice of identity element. So if you want a real number, e, such that when you multiply any real number by e, you don't change that real number, your only option is to choose 1 for this multiplicative identity element. But the inverses axiom then fails. And the reason the inverses axiom fails is because it has to be true for every real number that you can multiply that real number by something and get the identity element 1. But when you choose your real number to be 0, there's nothing you can multiply 0 by to get 1. So the inverses axiom is false. There is no number r, so lowercase r, such that 0 times r and r times 0 are equal to the identity, which, as we saw, had to be 1. Okay, so this is what stopped the real numbers being a multiplication under r. It was that the inverses axiom failed specifically for the number 0. The other two axioms were both fine. There is an identity element, and it's 1, and real number multiplication is associative. So the only problem we had was the lack of an inverse for the particular element 0. So what we can do is simply throw out the number 0 from the set of real numbers in order to get a set which is a group under multiplication. So this is what we do. We make a definition of r cross or r times like this, which is defined to be the set of real numbers except for 0. So that backslash you see there is the set difference that we met in the first part of 0007. So we make a similar definition for the complex numbers. So c cross or c times is just the complex numbers without 0. And if we do this, then r times is a group under multiplication, and c times is a group under multiplication as well. So we can check this. So there are the group axioms, and we know identity is true. So the identity axiom, so 1 serves as an identity element. Secondly, the inverses axiom. For every real number r in r times, so every non-zero real number, well, the number 1 over r is again in r times. The only time division ever goes wrong is when you're dividing by 0, but our set r times doesn't contain 0, so this is fine. And if we do if we do r times 1 over r, or 1 over r times r, we get back the identity element, which was 1. Okay, so the inverses axiom is true, and lastly, the associativity axiom. Well, again, it's just a fundamental property of real number arithmetic that real number multiplication is associative. Okay, we've checked all three axioms, so the non-zero real numbers together with the binary operation of multiplication do form a group. And similarly, the set of non-zero complex numbers, c times, is also a group under multiplication. Okay, so there are some examples of some multiplicative groups, which means groups where the binary operation that makes them into a group looks like some form of multiplication. Okay, let's move on and look at another example now, the trivial group. So this is a silly-seeming example, but it can be quite useful and quite important when you're looking for examples or counter-examples of various group theoretical statements. So the trivial group is a group which just consists of a single element. So the set, which we're just going to write down like this, so just one element called E, well, this has a binary operation. In fact, there's only one possible binary operation on a set with one element, and it's defined by E star E must be equal to E. So the set E together with this binary operation is a group. So you can check all three group axioms. It's very easy because the binary operation is so straightforward. And the name for this group is the trivial group. All right, so this is an occasionally useful example. Right. Okay, let's look at something slightly less trivial, which is the symmetric group. So you'll remember that we defined this in our earlier part of the module on permutations. We defined Sn, the symmetric group, to be the set of all permutations of 1, 2, 3 up to n. In other words, all bijections from the set 1, 2, 3 up to n to the set 1, 2, 3 up to n. Now, as we mentioned in our previous video, this set comes with a binary operation, which is composition of functions. So when you compose two bijections, you get another bijection. Therefore, composition of functions is a binary operation on the set of all bijections from 1, 2 up to n to 1, 2 up to n. Now, in fact, this set Sn of all these bijections together with the binary operation of composition of functions forms a group. So let's now check that. We have those three group axioms at the bottom of the page here. Let's check them one by one. So the first axiom the identity axiom, ID for short, well, I have to produce a permutation which satisfies the property that when you compose it on either side with any other permutation, you don't change that permutation. But there is a permutation which does that, namely the identity permutation. So if we take ID, I think that's what we called it in the first part of our course. So the identity permutation, which was defined to be the permutation which does nothing. So the identity applied to a number I is just I again. This thing satisfies S composed with the identity equals the identity composed with S equals S for any S in Sn, any permutation S. Therefore, the identity axiom holds, and the identity element is the identity permutation of this thing we've called ID. Okay, inverses. We need to check the inverses axiom. So, again, when we studied functions and permutations, we saw that if you've got a bijection, then its inverse is also a bijection. So if S is in Sn, then its functional inverse is also in Sn. And the definition of the inverse function is that when you do S composed with S inverse, or S inverse composed with S, you get the identity function. So that fact tells us that the inverses axiom holds for our set and binary operation. So finally, associativity. Well, function composition is always associative. Again, we verified this in the first part of the course. Therefore, in this particular case, function composition is associative, and so our binary operation is associative. Okay, so the symmetric group is actually a very, very important example, very important family of examples of groups, because you get one for each value of n. All right, let's move on now to another very important family of examples of groups, which is groups which arise out of our explorations of modular arithmetic. So again, I'm going to recall something which we studied when we were discussing equivalence relations at the start of this course. We introduced for each positive whole number n an equivalence relation on the integers called congruence modulo n. And the way you defined this relation was that two integers a and b were related, in which case we wrote a, then those three lines, b mod n, if and only if the difference between a and b was a multiple of n. So in other words, the number a minus b was divisible by n. So this turned out to be an equivalence relation called congruence modulo n, and we had some special notation for the equivalence classes under this relation. So the equivalence class of an integer a under congruence modulo n was written square brackets n, or just square brackets a with a subscript n, or sometimes, if we're feeling lazy, just a in square brackets. So for example, the equivalence class of 3 under congruence modulo 5 will be the set of all numbers which are congruent to 3 modulo 5. So all numbers which differ from 3 by a multiple of 5. So that's going to be an infinite set, but some of the elements it will contain will be, for example, minus 7. That differs by 3 from by 10 from 3, and 10 is a multiple of 5. Minus 2 is in there, that differs by 5 from 3. 3 is in there, 8 is in there, and so on. So if you don't remember this stuff so well, it would be a good idea to look over the earlier part of the course where we studied it, because this particular equivalence relation and these equivalence classes are going to be very important to us in the theory of groups. So we then wrote, we had a special name for the set of all equivalence classes under this relation, and what we observed was actually for equivalence, for congruence modulo n, there are only n different equivalence classes. And those classes are the class of 0, the class of 1, the class of 2, up to the class of n minus 1. So the notation we used for this set of equivalence classes was z sub n, and the name was the integers modulo n. All right. So Zn is our set of equivalence classes under this relation, and in fact it turns out that any equivalence class is equal to one of the equivalence classes, class of 0, class of 1, up to class of n minus 1. Now this set, the integers modulo n, comes with two binary operations, so one of which is derived from addition and one of which is derived from multiplication. So here are the definitions of those two equivalence classes. Of those two binary operations. So we can define addition of equivalence classes by defining the class of A plus the class of B to be equal to the class of A plus B. And we can define the product of two equivalence classes, so the class of A times the class of B, to be the equivalence class of A times B. Now, there are some issues around this. It's not completely obvious that this definition makes sense or that it's well defined. The problem is that, for example, the equivalence class of 3 modulo 5 is the same as the equivalence class of 7 modulo 5. So if I change this A to be 3 or minus 7 or minus 2, I've got the same equivalence class over here. So do I always get the same equivalence class over here as the sum? Well, this is turns out to be true, and you can read more about this in section 4.2.1 in the online notes. But for now, let's just try doing some examples of these binary operations. So for example, let's take the equivalence class of 2 modulo 5 plus the equivalence class of 3 modulo 5, and then by definition this is the equivalence class of 2 plus 3 modulo 5, so the class of 3 modulo 5. And of course, if you want, you can rewrite that as the class of one of the numbers between 0 up to 4, since we know that actually every equivalence class is equal to the class of 0, 1, 2, 3 or 4 in this case. And in fact, this will be equal to the equivalence class of 0, as 5 is equivalent to 0 modulo 5. On the other hand, let's do a multiplication. So if we look at, let's say, the class of 2 modulo 7 times the class of 6 modulo 7, well, our definition is that that is the equivalence class of 2 times 6, 12 modulo 7. Okay, this is fine. But also we can, if we want, write this as one of the equivalence classes 0, 1, 2, 3 up to 6. And in fact, this will be equal to the equivalence class of 5 modulo 7 because 12 is equivalent to 5 modulo 7. Okay, the difference between 12 and 5 is a multiple of 7, and therefore they're congruent mod 7, so they have the same equivalence classes under the equivalence relation of congruence modulo 7. Okay, so it turns out that a very useful fact is that Zn under addition is always a group. Okay, I'm going to highlight this because this is something we're going to use fairly often. It's a very useful family of examples of groups. But we have here two binary operations, right? We've got the binary operation of addition, and we've seen that Zn is always a group under addition. But on the other hand, we've got another binary operation, multiplication, and in fact Zn will never be a group under multiplication. And the problem will be, similarly to the problem we had with the real numbers, that there will be elements which don't have a multiplicative inverse. So the equivalence class of 0 will not have an inverse when the binary operation is multiplication. So just like for the real numbers and for the complex numbers, we can get a group under our binary operation of multiplication, but to do so we have to throw out certain elements. So we have to throw out the elements under which don't have inverses. Now, unfortunately, this only works when you have a prime number p. So when you're looking at the equivalence class of congruence modulo a prime number p. So when p is a prime number, here's the definition we make. We take z cross p to be the set of equivalence classes 1, class of 2, class of 3, up to class of p minus 1, modulo p. So this definition is only when p is a prime. Now in this case, what we get here is a group under multiplication. So when p is prime, the set zp cross, so all of the equivalence classes except the equivalence class of 0, is a group under this definition of multiplication of equivalence classes. Okay, now is a good time to go and practice some of these definitions. So what I suggest you do now is pause this video and have a go at the exercise on modular arithmetic on problem sheet 9. So try that, try some additions and multiplications, get familiar with addition and multiplication of congruence classes, because we're going to be using those things a lot. So finally, a word about the title. Modular arithmetic just refers to addition and multiplication modulo n. In other words, these binary operations of addition and multiplication, which we've just defined on the sets of equivalence classes modulo a particular number n. Okay. So let's just say, actually, before I move on to our next example, there is something slightly mysterious here, which is how do we find inverses for elements of the integers modulo p under multiplication? It's fairly simple in the additive group Zn together with the binary operation plus, but in Zp times, this is something slightly more mysterious happening here. So, for example, let's have a look at the integers modulo 5, so the multiplicative group Z5 cross. So there we could take, for example, the class of 2 modulo 5 and the class of 3 modulo 5, and if we multiply them together like this, well, what I get there is just the class of 6, and that's the same as the class of 1. But of course the class of 1 will be the identity element in this group. When you multiply anything by the class of 1, you don't change that thing. So what we found here is an inverse for 2 and an inverse for 3. Namely, 2 is the inverse for 3, and 3 is the inverse for 2. Okay. Let's move on to another family of examples now. So here we're going to talk about matrix groups. So the set of all square matrices m n by n over, let's say, the real numbers, well, this thing has a binary operation namely matrix multiplication. So if you have two n by n matrices, you can always multiply those things together. You get another n by n matrix. So matrix multiplication is a binary operation on the set of n by n matrices over the real numbers, for example. But m n by n of r together with matrix multiplication, it's not a group. And the reason is the same reason we keep seeing. It's not going to obey the inverses axiom. So the problem we've got, just like the problem for the real numbers under multiplication, is that some elements of the set don't have multiplicative inverses. For the real numbers under multiplication, there was no multiplicative inverse for 0, and for the n by n matrices, the situation's even worse, because there are lots of square matrices, not just the 0 matrix, which fail to have multiplicative inverses. So what we need to do is we need to look at the set, we need to restrict ourselves to the set of only those matrices which are invertible, and there is special notation for that set. So here GLNR is the set of all n by n invertible matrices with real entries, and GLNC is the set of all n by n invertible matrices with complex entries. So once we've made this definition, GLNR is a group under matrix multiplication. And the identity element, of course, will be the identity matrix. And of course, the same thing applies to the group of complex invertible n by n matrices. GLNC is also a group when the binary operation is multiplication. And again, the identity is the identity matrix IN. Okay, if you're wondering where GL comes from or what GL means, well, the answer is GL here stands for general linear. So you'll see these things called the general linear group. All right, last slide then is about group tables or Cayley tables. And group tables or Cayley tables are just a way to display a group visually. So what we do in a group table is we have the rows and columns of a table labelled by the elements of the group, and in the row labelled by the group element I and the column labelled by the group element J, we put I star J, where star is whatever our group operation is. So let's, before we actually do an example, let's just flag up one thing which is important, which is, in general, it matters which way round you do the binary operation. I star J might not be the same as J star I. For example, in the symmetric group in general, or in the general linear group in general, the binary operation you've got there is not commutative, so the order matters. So it's very important that we remember when we're doing our group tables that in row I and column J, we put I star J that way round. So let's work out the group table in a particular example. So the group we're going to look at is the integers modulo 5 under multiplication. So actually we have to take the non-zero equivalence classes, so the class of 1, the class of 2, the class of 3, and the class of 4. That's what Z5 times means. And our group operation is the binary operation of multiplication, which we introduced a couple of slides ago. So here's our Cayley table. You can see the rows and columns are labelled by the elements of this group. You can see I really have omitted the subscript 5 on these because I was feeling lazy. And in these in the entries in the table, we have to put the products in this group. So for example, here in the cell in row 1 and column 1, I have to put the class of 1 times class of 1, which is equal to the class of 1 times 1, which is equal to 1, the class of 1, of course. So here we should fill in the class of 1. And of course the first row is just going to look like here we will have the class of 2, and here we will have the class of 3, and here we will have the class of 4. And the reason for that is the class of 1 is the identity element in this group. If you multiply the class of 1 by the class of whatever, you don't change that, because 1 times any number is just the same number again. So in the first row and in the first column, we will have 2, 3, and 4, just like this. Okay, so where it gets interesting is in the other remaining elements in our table. So let's work out some of the elements in this table. Let's pick some of them and work them out. So we'll start out here with this cell here. I'm going to ring this in blue, and we're going to do the calculation in blue over here. So here we should look at, we're in row 2 and column 2. So the entry is the product of the class of 2 and the class of 2. That's the class of 2 times 2, in other words the class of 4. So here we should put the class of 4. Okay, let's do another one. So this time we're going to do this in orange. Here we go. In this cell of the group table, well, this time I'm in row 2 and I'm in column 3. So what I have to put in that table is the class of 2 times the class of 3. When I work that out, of course, I get the class of 2 times 3, which is the class of 6. And we can rewrite that as the class of 1. Right? Remember, we are working with congruence modulo 5. 6 and 1 differ by a multiple of 5, so they're congruent mod 5. So that means the equivalence class of 6 and the equivalence class of 1 will be the same. So in here, I can put the class of 1. Now, of course, in our group, 2 times 3, and rather the class of 2 times the class of 3, and the class of 3 times the class of 2 will both be the same. So I can put the class of 1 here as well. Okay, let's work out some more. So here in dark green, this cell is going to be in dark green. So here, in this cell, I should put the class of 2 times the class of 4. That's the equivalence class of 8. And 8 is congruent to 3 modulo 5, so I can write that, if I like, as the class of 3. So here we should put the class of 3. And again, 4 times 2 and 2 times 4 are the same, so I can put the class of 3 here as well. Okay, last few. Well, 3 times 3 is 9. 9 is congruent to 4 modulo 5, so I can put a 4 here. 3 times 4 is 12, and that's congruent to 2 mod 5, so I can put a 2 here. 4 times 3 is 12, so I can put a 2 here. And lastly, 4 times 4 is equal to 16, and 16 is congruent to 1 modulo 5, so I can put a 1 here. And now I've completed my Cayley table. And the good thing about these tables is that now we have complete information about the binary operation in our group. We can look up absolutely any value that the binary operation takes, because every possible multiplication modulo 5 is found somewhere in our table. So we've got complete information about what the group does in this convenient format.